Welcome everybody to another IOE professorial lecture. Good evening, everyone. There is no online access to this event, so everybody's in here. Welcome. I'm Li Wei. I'm the Director and Dean of the IOE, so I'm very pleased to host this evening's event. Now, today's lecture is on school mathematics in the digital age. Math education is always a time-enduring topic, but math education in the digital age is a really timely topic. And today's speaker is Professor Alison Clark-Wilson, Professor Research Fellow in our Department of Culture, Communication, and Media. Now, as some of you may have already seen in Alison's biography, she's a former secondary school teacher, maths teacher, and as a teacher and academic, she sought to harness cutting-edge technological innovation to improve learning. Typically, her focus has been on learning in mathematics. That most high stake and for many most challenging topic to grasp. Alison will talk about her esteemed research captured in now over 70 publications, including 5 monographs and edited volumes. Now, in introducing Alison, I'd also like to note her parallel success in translating that knowledge for the direct benefit of teachers and pupils, either directly or through her extensive work with edtech industry. In that respect, too, Alison's work has been outstanding and a real example to academia more generally. At IOE, her enthusiasm and generosity in sharing her expertise in what we now call engagement and impact, bridging the gap between researchers and potential users of their work, has been very much appreciated by colleagues. Alongside, Alison co-founded the Global EdTech Testbed Network, which aims to support more sustainable and scalable approaches to the development and adoption of EdTech. Characteristic of her wider approach, that work too draws out the voice of teachers and voice of learners to ensure their needs remain at the heart of EdTech innovations. Alison, thank you very much for taking the time to share your fascinating work, and really, really looking forward to hearing your lecture. Over to you.
Thank you very much, Professor Li Wei, and thank you to all of you for taking the time to come along. Over the next 50 minutes or so, I'm going to take you on a nearly 50-year journey through mathematics education, school mathematics education, with a focus on England. And it's to tell you 2 parallel stories. One is the story of how I came to be a professor at University College London, which is a surprise, but also how over that period digital technologies have, or maybe have not, impacted on the sort of school education that we are seeing in schools in this country and around the world right now. So much of it is going to focus on the concept of innovation in education, thinking about doing things differently, doing things in a new way, taking advantage of the way that our society and culture and the technology moves on. But at the same time, we'll be thinking about the longer term implications of that. What do we do when we do find things that are promising for our education system? How do we ensure that they are taken up and used and exploited in ways that do benefit the learners at the end of the day in our education system? Now, I have got a warning. For some of you, the topic of this study, of this talk, mathematics, is going to trigger memories from your pasts. I know a lot of you. It hasn't always been a smooth ride. So what I really hope that you go away with at the end of this evening is a bit of a therapy session to help you rebuild that relationship with mathematics. And I hope that some of the examples and some of the work that I'm going to share with you this evening will help you to see that maybe not for you, but for your children, grandchildren, great-grandchildren, we need to still be advocating for things to be done maybe a little differently than they are currently in our school system. And the other thing is, please be prepared to do some thinking. Okay, so if you thought you would come here, just sit back, end of a busy day, I'm going to be asking you a few things. Nothing too taxing, I can assure you. So let me just talk through the structure. I'm going to start with a little bit of an autobiography with respect to a topic that I just love, which is humans, tools, and hands. And I'll explain a little bit how I came to be slightly obsessed with tools and tasks and things we do with them, with our hands. I'll move on to talk about creativity and curiosity, beginning with my own, but then thinking about what that means in the context of schools, schooling, and obviously mathematics education. And then we'll move to think how things might be done differently if we have a slightly different view on the way we see mathematics and our relationship with mathematics. We're going to see things moving. And then I'll finish the talk really talking about some of the challenges that we face in our systems as we try to keep up with technological change, which is wrapped into our societal change, our cultural change, all the things that impact on the way that we might take a future education system that maybe does things a little bit differently in mathematics. So let me just mention a little bit about my background, because I don't come from a family with a long history of academia or working in highly skilled professional trades, but I do come from a long background, 3 generations of mainly Londoners who did a lot of things with their hands. They built barges, they were naval engineers. We have a long line of Fleet Street printers who were working at the coal face of technology when the printing industry was really at its height. Seamstresses, we're all knitters. But this idea that our hands and the tools that we put in those hands are really quite culturally embedded in what we do, to the extent that we're a bit nerdy when it comes to tools, and particularly since the technology arrived. If we bought tools, they stayed in their boxes, or they got nice labels and bags, and they were very much looked after and coveted. And we were quite aware of how the tools that were around us were evolving. So we were probably quite an innovative, outward-looking family with respect to things that made tasks more efficient, or tasks maybe got a better quality of output. We were always on the lookout for that new gadget or tools. So let me tell you about my mathematical toolkit. So I'm going to take you back to the 70s, when pretty well this was a standard toolkit. I mean, those of you around my age, you've got your standard protractor and your wooden ruler and your very, very wobbly compasses. Yeah. Very wobbly ones, very difficult to do anything with them. They were never tight enough. You never quite got the accuracy you wanted. I came from a family that loved tools. So do you think my toolkit looked like this? No, of course not. I had one of those. It was so much more sensible. Never quite fitted in the pencil case, but then I made a bigger pencil case to accommodate it, so that was fine. But there's a subtle difference between those two tools that really conceptually help you understand what angle is all about. How many of you who are teachers in the room spent the first lessons teaching children to use a protractor, really trying to help them not see the bottom of the bit of plastic as the bit that... Now, that's a flawed tool in my mindset, because we never fed back to the manufacturers of those protractors. That is sustained now. I mean, it's madness, right? What about the wooden ruler? What replaced it? Well, a Perspex one. You could see through it. You could see what you were trying to measure. You could see what was underneath the work that you were working on. And then, of course, they were engineers in my family. So I got one of those. It was obvious. You adjust it. It doesn't move. You have a lovely little sharp pencil point. You could be accurate. So that gives you a sense of this slight obsession with having the right tool for the job. And let's keep that in mind as we go forward. So the other big tool I had in my toolkit when I started out was these. Come on, I love a show of hands. Who remembers these? Yeah, we just age ourselves instantly, okay? Thank you. For those of you who don't know what that thing on the left there is, it's something called a book of logarithms and exponential trigonometric tables. And before we had other tools, we used to have to laboriously use these. So it probably added about 7 minutes to a calculation, I would say. By the time you'd look things up, check them, what you did when it was a cube root or it'll come back to some of you. I think I could probably still use one, but I haven't used one for probably around about 40 years. So what replaced it? Well, I was from a school of a group of engineers. So even though we had log tables in the school, I had a slide rule, which is brilliant. I mean, how many of you learned to master a slide rule? Yeah, it was better than the logbook. Yeah, but we could do better still, because in 1977, the first one of these appeared on the market in the UK. It's still here, and it still works. Wasn't I lucky? It was a bit of serendipity, because I was in the cohort of young people in the UK who were first allowed to use a calculator in the additional maths and A-level exams, 1978, 1979. The rules had changed. We could take a logbook in, but if we had one, so this wasn't available to all, we could take a calculator in with all of the affordances and advantages that had. But in my setting, I was probably one or two students in my class, which was only 8 girls in a South London comprehensive school. My teacher was not interested. I had this shiny new tool. It had lots of buttons on that, although very limited when we look at it now, were really quite revolutionary in the time. And I wanted to know what every single button did. So I did read the manual. I'm one of those. Yeah. And I found out what every button does. And the secret buttons that really unlocked bits were store and recall and exchange. And they were so simple, but they just allowed you to sort of park things, bring them up again, and actually do some really quite creative numerical work as well. So that one's there. And then, because my dad liked a bit of technology, we got one of these. Anyone recognize the Sinclair ZX81, one of the first sold to the public computers? It actually didn't arrive with a screen, which was a bit of a problem. Can you imagine computing without a screen? But do you know what? My first program ever was to write a program to solve 10 Pythagoras questions from my O-level textbook, because I realized there were 2 types. It was a basic, are you finding the hypotenuse, or are you finding one of the other sides? A simple program. I could check my answers, because there were no answers in our textbooks in those days. It was outsourcing, it was helping me be more efficient, and it was giving me feedback. And it was a bit of fun along the way. So in between leaving school, engineering degree, the technology is moving on at quite a pace. And when I found myself down at the very famous Mathematics Centre in Bognor Regis, which is now part of University of Chichester, where I went to do my teacher training in the early 90s, I didn't know that it was the hotbed of digital technologies in mathematics education globally. The tutors who were training me to be a teacher were really at the cutting edge of innovation. So when I arrived there, technology came at me from every single direction. So from graphing calculators to starting to mess around with computers, and at that stage it was still programming. We didn't have graphics cards. We wanted an image on the screen, we had to write a program to get it there. And I really had that great opportunity over the course of a 2-year PGCE, which gave us a little bit more thinking time and experimental time, to start to create activities that I could then take into my classroom. So one thing was getting familiar, having time to play. The next thing was really being able to say, right, okay, I think I'm ready to give that a go in a classroom with real children, which is scary. Yeah, for any of those of you who've never taught, it's challenging enough to stand up in front of teenagers in your average maths lesson in a comprehensive school anywhere in the country. Bring out the technology and the risk level goes up quite high. Okay, so one of the first activities that I developed, I mean, the context is there. My daughter Laura came home with a homework. She was in year 4. She's 35 now. And this homework was your bog standard draw a coordinate picture diagram. And it may be a familiar activity to some of you. And I just thought, oh, this is a bit tedious, Laura. Should we try and do it on the graphing calculator? So out comes the calculator, and we had a go. And then I realized, well, we could make this dog move. Never mind a static dog on the screen. We could actually make this move. Now, this is at a time of Tamagotchis. So those of you who remember the Tamagotchi little digital toys, which involved keeping a little very pixelated digital creature alive by doing things to it. So, you know, our standards of graphics were in a very, very different place here, I have to say. But I took that idea and I took it into the classroom with my year 8 class, and they flew with it. And that's a good example when you do that risky bit where you really don't know if the students are going to respond well, whether they'll persevere with some of the button pressing and inputs you need to do to begin with. They persevered, and interestingly, I've got the work of Daniel Firmage on there from year 8 in where was I there? Admiral Lord Nelson School in Portsmouth. I was really aware of the ethics of, sorry, that was the microphone. I was really aware of the ethics of showing his work. So I was very able to contact him last week and say, hi, Daniel, I hope you don't mind, but I'm doing a bit of a presentation next week and I'd love to show your work. Do you mind? I got a lovely email back. I'll tell you over the drinks later what he's up to now. But however, he said, I remember that lesson, which is interesting. Let's hold that thought. Let's hold that thought. So that lesson with those very early tech devices, and a little future thing for everybody now is that's still the only device that you're allowed to take into a formal examination now. Okay, that's 1999. That's the tech students currently are allowed to use in the school system. And then I did one thing which I'd never done previously, was I wrote it up. And this is something that as teachers, you know, when do you get the time to really tell other teachers about what you're innovating with or what you're doing? And I was encouraged by other people, you should write that one up and send it off to Micromath. And that was the very first time that I'd really shared outward something that I tried in my classroom, and I got great feedback from it. It was a really interesting moment where other people noticed it. I was then asked to present things at conferences. Could I trained other teachers with this little approach, and that was very much the beginning of seeing that probably I really enjoyed sharing my practice and supporting other teachers to take on the technology and think about how it might impact on their own. But these little tiny feedback loops are really, really important. So around that time, I went to begin my master's degree. I'd been hooked into reflecting and thinking about my teaching. And I was doing a module on technology in geometry. And one of the tasks that we were working on was taking a very classic book. I've got it here because some of my mathsy friends will like to look at it later, which interestingly was published the same year I was born. I thought that was serendipity. And in here, there's a paper and pencil construction for a shape, and we were taking the paper and pencil idea and thinking about, let's have a go and see if we can do that on this very new thing called dynamic geometry software. So this was something that arrived in the 90s, and we were really experimenting with what could we do with it. So I'm going to switch technologies here to a document camera. So you're going to be able to watch my hands, and hopefully we're here. So ideally, you would all be sitting on a paper circle, I should say, but we don't have time for that. So I will lead this from the front. I've got a circle of paper here, And the way this goes is we put a point anywhere on this circle, and I'm going to go somewhere over here, okay? Bit of a thought experiment now, because what we're going to be doing is picking another point anywhere on the circumference. So I'm going to pick one over here. And then the way the construction goes is I'm going to fold the paper so those two dots just touch. And then when I unfold, I've basically got a fold line here. Now, if we were to keep doing that, so I'll put another one a little bit further away and do the same again. You probably can just begin to see that the fold lines are doing something that could be potentially interesting. And if we were to go all the way around the circle, repeating that, folding and opening out again, we would see something emerging in the middle. And we call these envelopes of folds, where we actually look at how different mathematical shapes come about when we do lots of different interesting folding activities. So I'm not going to carry on with that one, because what we did in the master's session was, let's just switch technology. We started to construct it using this new thing called dynamic geometry software. So what I'd like to do now is lead you through what that looked like, and we'll see what surprises might come from that. So I'm going to try and replicate what we did there. I sort of put a dot somewhere about that, and then I had this dot that was my imaginary point that I folded over. So if I were to, and you have to use this brain exercise, if I was to fold that dot over, then I ended up with a line that was sort of down here somewhere. Yeah? Okay, so let's have a think about, if we were to join that dot with another line. I've got some mathematicians in the room, which is really helpful at this point in time, but this fold line goes through a particular point on the new line I've drawn there, which has got a name, and I'll let some of my friends help me out with the name of that. Go on, Nicola, I can see you're dying to tell me. It's a midpoint. Thank you. And in the software, it knows these sorts of things. So this software's been designed to let us do the sorts of things that we might want to do mathematically. Now, if we now think about what the fold line was, there's another nice mathematical phrase that for those of you for whom the mathematics is a little bit nearer to your current thinking, may remember as a perpendicular line. And I'm going to make that perpendicular line a little bit dotty so that it doesn't distract us too much. But I think I'm going to just hide these other two, because we kind of put those on to get us where we needed to be. If I now move this dot, I think you can see that my dotty line, that's the fold line, is also moving. And it's moving weirdly, if I'm honest, isn't it? I mean, not really much. Some of my mathematicians will get a sense of what's going on. But there's another tool here which will help us catch the trace of those dotty lines. So if I ask this software to show me the trace of the line, this is going to be really helpful to us. Because as we're moving round, we're definitely getting a curve. Well, there's no surprises there. It was the book of curves, after all. And I know some of you know what that shape's called. But let's hold on to that for a moment, because have we got any conjectures? And that's one of my favourite words in the maths classroom, because it's a big word for learners. But what do you think? Any ideas around what's going on here? Do we know what that shape is? Richard, can you help us? I'm going to go back to Nicola.
Oh, no. Somebody said over my shoulder somewhere, ellipse.
Ellipse. Okay, so we've got, so those of you who've got some names of curves out there, this one could be an ellipse. Now, we've got really a static example. I know I was able to use my imaginary fold lines to show you what the whole thing would look like, but we can go better than this. So I'm going to erase my traces. So so that they don't keep tracing. And I'm going to stop tracing my perpendicular line because I want to approach this another way. We have a mathematical idea called a locus. And some of you will know the concept of a locus. But a locus is when we think about what the path of something might be when there's some other constraints. Now, we were just looking at the path of that perpendicular line, that dotted line, as I dragged the point around the circle. Now, the software will construct that for us. So what we can ask the software to do is, please, would you draw me the locus of this line as I drag this point around the edge of this circle? And what the software will do is construct the locus. Now, why? It's nice, isn't it? It's nice. Why might we do it that way? Because I can now conjecture a little bit more. Because I've constructed the locus, I can think about what happens as my original point goes really near to the center. And he conjectures what's going to, what shape do we all think we've got now? And who can actually come up with a justification? Now, we haven't got time to do the whole maths lesson, and I am going to move on. But what I want to illustrate here is we've now got a dynamic scenario that came from a very simple, accessible paper folding exercise that has allowed us to make conjectures, think about what some of the language or some of the properties might be. And then the bit that really sold me that this software was a good thing is the one thing I couldn't do with my original construction is see what happened if I had a point outside the circle. So shall we go see what happens? Well, it's an O, isn't it? It is an O. No matter how many times you see it, it's an O. And that's just one of the curves in the book, okay? So that is my retirement project, by the way, to digitize that book, but not yet, not yet. So my point in really sort of laboring that particular activity is we all need to have that inspiring moment when we really see the value of an innovation. It happens to be a technological innovation, but an innovation, we have to have a reaction to it. So hold on to that thought, because we've got two things going on here. I have no doubt that learners who are open to ideas, particularly in their schooling, they're in the right place for this. But obviously, in order for learners to have access to tasks like this one, we need to have worked with and supported the teachers. And their experiences will have been very, very different. So we'll come back to that. I'd like to just go on and show a couple of other activities that give you sort of alternative bits of maths that are made very accessible when we start to think about mathematics in a more dynamic way. So I put a very tantalizing point here, which says drag me. And of course, that's what children will do if you present something like that to them. Very limited representations there. Just got a number line with some numbers on it. And I'm going to drag. Oh, that's interesting. Oh, what's going on there then? Hang on. So I'm dragging the red one that says drag me, and the other one's getting away from me. What happens if I go the other way? OK, it's intriguing. You're curious. OK? How you might, if you were driving this, start to rationalize what's happening, maybe make a conjecture, is why you need to be hands-on with the technology. And watching a teacher do is never going to be enough. It's frustrating. So I'll take a couple of conjectures, and then I'm going to move on to one that's a little bit more difficult. And I'm going to give you some clues, because I'm going to drag it to 5. And you've got an output there. And I'm going to drag it to 10. And you've got an output there. And then this is good because it makes us think about what's going on when we go the other side on the number line. Some of those rules you used to know that didn't make much sense, yeah? So I think we've probably got a sense that this is a doubling engine, yeah? Okay, so we've got a doubling engine. That's a little bit easy. So let's go for something that's a little bit... Oh, okay, hello. Oh, I'm chasing you. Oh, you're running away again. This idea is playful, you're curious, and what's going on underneath here? Well, this one's very weird. Why is it so weird? doesn't want to go left, if we just use really simple language. Yeah, it only wants to go right, and it doesn't quite want to give me a kiss. It just wants to, there's a story there, there's a narrative there. Children would tell that story with something like this, how these two numbers behaving one against the other. So why would this even be relevant to, I mean, it feels very simplistic and basic. Well, let's think about what's really going on here. So I've got the same, let me just move this over a little bit. I've got the same situation here, so I've just moved it to another screen with some more representations. So there may be some of you with some hunches around what this function is or what this relationship is. What I want to do is I'm going to hide the dot that was the output because I'm going to put it in a different place. And you might think, why on earth has she put it there? Well, if I give you that, you might see a little transition there. So what does it mean if we don't plot the output on the same line? What if we plot it in a different direction? Well, where's this heading? And I've got a trace on it just to... Okay. So is that shift an interesting new representation for some of you? Yeah, so that's innovation, yeah? Innovation is just having that idea that says, well, okay, we've done loads of those along that way. Why don't we think about this in a different way? And this opens up a whole door of algebra, mathematics, which is coming at a very accessible level, but by having the different representations really enables us to make some challenging ideas much more accessible for our learners. A little bit of geometry, and then I will take you to somewhere else. So more ideas that we meet a lot. You know, there are a lot of rules in geometry that many of you learned and many of you forgot and many of you are trying to teach. And one of the rules is to do with the external angles of shapes. And we've got all sorts of metaphors to help us remember the external angles of shapes. And I just thought it'd be interesting to play around with different ways of thinking about the external angles of shapes. So it's very common that we sort of imagine lines around the edge. So we sort of think about the external angles as being something to do with walking around the shape, or that, you know, we have these sort of metaphors of what does it mean for a shape to have an external angle. So if I highlight where the external angles are now, that's how we define external angles. They're external to the shape. There's a lot to discuss there. Are they fully external? However, I've got this intriguing drag me. So is this an image that you've had to think about external angles? And because it's dynamic geometry, it's only working because it's in the centre. It's definitely only working because it's in the centre. Does it work there? What happens if it goes, oops, sorry, let me just grab my point. Never use technology live. Come on, point. You come in. Oh, that's because I've got that showing. It's all right. That was a hiccup. We'll come back to those in a minute. Doesn't matter where that point is, and it doesn't matter where I go, they're still going to add up to 360. And I mentioned hiccups because it was a little area of my life where I spent a lot of time looking at the things that go wrong in the classroom when teachers are using technology. And my PhD study really focused on those things that really prompt a teacher to reflect on something that is mathematical, pedagogical, meaningful. So not just that the projector won't work, but when you're using software like these, which are inherently mathematical, things happen that if you haven't met that situation before, it's either going to be something you don't want to ever do again. Yeah, that's a problem for us. Or if you have support to have a reflective conversation around it, it's an opportunity for you to learn and develop your practice. Another hiccup that might happen in this activity is if I do that. All feels a bit broken, doesn't it? Not time. We haven't got time to discuss it now. Is that the maths that's gone wrong? Or is it the construction I did wasn't quite right? But we need to talk about it, but not now. And then very finally, I want to show one more geometry activity. Again, this is the bread and butter of secondary mathematics, these topics. It's the stuff that kids are schooled in, they have to solve problems in relation to, and one of the things they rarely get the opportunity to do is to explore these concepts before we arrive at the rules. So you've all seen triangles before. You've all seen angles coloured and shaded, and I'm deliberately not putting numbers here, okay? So that's another thing you'll notice. My representations are really quite simple, but let me put a few more lines on. Right, we're good with these extra lines now, aren't we? We can see when we put these rays or these extra lines that extend the sides, it lets us see other things about the shape. So we're all good with that. I've just put some extra lines that have elongated the sides of the triangle. Why might I do that? Ooh, have a look at that. Tell me what you think about that now then. Are you convinced? Are you seeing some rules and some things you've taught or learned about opposites and parallels and transversals and all those sorts of things? But this is my favourite reveal. Because when we look at one triangle, the idea that a triangle which tessellates on a plane has all of these properties that actually explain so many scenarios, and because I'm dynamic, I'm not going to break it. If students are experiencing, learning about angle and shape, touching the technology, dragging, really key thing we were doing there. I was around at the time of the beginning of the whiteboard revolution. For me, oh, sorry, Teresa. Very passionate. For me, the whiteboard was one of the most amazing bits of tech in my classroom because my kids came out to drag things that were mathematical at the front of the class. I wasn't using it to press forward on my PowerPoint. It was about engaging tangibly with the mathematical objects that we were working with and working on. So I'm going to leave geometry and just come across to another area that we've worked extensively on, and many of my colleagues are in the room, which is lovely. I think we'll start with Shaky. So Shaky's a very famous robot because, yes, he's in our lovely UCL Cornerstone Math software, but he was actually the first robot to be built at MIT in their AI lab. And Shaky was so named because he did shake. Okay, now our Shaky's not so shaky in terms that he doesn't shake, but he does move. And this is an activity from a set of resources that were developed over, in all, 7 years of staged research projects. And these were really there to introduce students to something we call multiple representations. And the idea of multiple representations is that we've got something contextually interesting. That's Shaky. And we've got a number line here, but our number line is measuring Shaky's distance. And we haven't got points chasing each other anymore. Our world has changed. We've got the timer, yeah? And the timer there is telling us how far or where Shaky's position is after each second of his movement. We've got something going on down here with a graph. We've got some values that just appear and highlight. And we've got this interesting thing called an equation. Now, traditionally, the way we taught equations, you've always needed to start with the equation to produce the table of values in the graph. That is our bog standard method. Here, we're kind of not bothered about that for a bit because there's so much for us to notice, make connections with, relate in the images we've got there. And of course, it all gets really exciting for students when we have the opportunity to edit, and I'm going to do a quick edit via the graph. I've got a whole host of ways to edit here. Let's go with that one. Okay, anyone want to predict what's going to happen to Shaky? And of course, when the students get hold of this, they have far more interesting scenarios than the one I've just created there. But These are resources that are designed for students to be hands-on with handling the mathematics, really supported by the teachers to make sense of and make the connections between the maths that we need them to do for the current school exams and the sort of activities that really build that conceptual development. And the direction of travel, well, we can bring two characters in. We've got a scenario here where their paths cross. We're into simultaneous equations land, but it's a very different context, the highly pure maths algebra way that most of our school textbooks and our EdTech products address. And it's a way that really invites students to engage with the deep mathematical ideas that are there. So let's come back to the slides. One of the big challenges that we have, we've always had this challenge, but it feels urgent right now, is how we think about what we actually value in mathematics learning. So a lot of what we value is the outputs of students' examinations at the high stakes stages of the end of age 16 or 19. We don't necessarily value the experiences that they're having along the way. So even in those few activities we've just had a look at together, we've done things like, we did dragging, but we were dragging mathematical variables. Yeah, we were really interacting with the mathematical ideas, and this new thing of dragging, which has only been available since we've had these technologies, is, in my view, a very, very significant act when we're trying to support young people in their learning of mathematics. We were modelling. We took a paper circle and we created a mathematical model that enabled us to test that model. I've done that a few times. It was pretty successful. It would have been messier and we'd need a bit longer if we were doing it ourselves. But you would have got there, and along the way, you would have thought about in your model what was working, what wasn't working. And modelling is a really key 21st century skill. I think it's always been a human skill that we all do in our day-to-day work and lives. Making conjectures, critical mathematical skill. If students don't have opportunities to make conjectures because they're kind of always told what needs to happen or what they need to do, how do they really start to get that feedback? And this is where the technology and the feedback it gives you is so powerful. If you make them, you've got to test them. And then you might need to justify whether it works or whether it doesn't work. But you can only really do this when you've got tangible, real, meaty problems to work on. So one of the challenges we have is in many curricula around the world, we're heading for an endpoint, which is a timed written exam, which is very short, quite small focused questions that doesn't let you even get into something a little bit more meaningful. And that kind of drives what goes on in classrooms. We could go on. So I'd like to offer you today my healthy maths learning plate. And I've really drawn on the ideas of Diana Laurillard here, who has the conversational framework that really thinks about, let's think about what learners need to do in their experience of learning mathematics. And this is a list, and it's a starting point, and it's not tested theoretically. And if anyone is taking pictures and putting it anywhere, you need to say that. This is not a theory. This is a conjecture. And my conjecture is that as part of a healthy maths learning plate, learners need to have opportunities to explore concepts collaboratively and independently. Yes, they need to practice test exam questions. Yes, they will need to drill and practice some skills towards those. They probably have to listen or watch or be guided by a teacher at some point. And in my view, they should be producing some mathematics at some points in that journey. And for me, producing mathematics isn't necessarily the answer to the 3-minute test question. It's something a little bit meatier. And then we can think about what the plates might look like. So here's one that might fit in Key Stage 3. No big high stakes exams there. Lots of time for exploring concepts, maybe not so much time drilling and practicing or prepping for tests, they're a little bit way off there. But could we really think about what that mathematical diet looks like and what it might look like at different times in our schooling systems? And obviously, when we get nearer to high stakes, it will change. We haven't got time for the explorations, but we would hope they've been done. Okay, so this is just something to play with, to really think about if we have a very learner-centred approach to school mathematics in this country, what might a balanced plate look like, and how might that balance change as we move through the phases or for particular parts of the curriculum offer. And because I was thinking about dietary metaphors, I was reminded by this table, which is, it came from a government-funded project that led to the Better Maths report back in 1987. And this was really critiquing what was going on in textbooks. And it gave you the junk food, junk mathematics analogy. So your junk food, prep's done by someone else. It's all simple and laid out in steps. It's superficially attractive but lacks flavour. All the real nutrient is removed, and you've got substitutes. Okay, and the parallel there was, this was 1987 and textbooks, but I'm going to replace the word textbook with EdTech. That is the current offer in the educational technology that many schools are using right now. So I'm sorry to say, but see most EdTechs. Most of the nasties are removed. It looks structured, taking me on a pathway, sending me from A to B to C. If I got that wrong, it's sending me to D. Nice rules-based algorithms in there. Probably doesn't get retained. And often there's no real-life situations or context. So this is a real-life situation, everybody. Not all real-life situations are applicable in the real world. It's as real to engage in something that piques your curiosity and gets you into something that is in the curriculum. But this idea of where's the real context for which our young people will engage and want to pursue mathematics through their lives, not necessarily as a subject to take as an examination, just have a better experience and a more positive attitude, and see what opportunities mathematics enables you to avail. So as I bring this talk to a close, there's some really profound documents out there right now looking at the future of education and skills globally, because there is a global sense that our current timed written high-stakes examinations of the type all of you sat are rather outdated, to put it politely, and that they don't measure what we value, and they don't then offer students rich experiences that contribute to them developing the sort of ideas that we think are important. Curiosity is key. Dynamic technology really helps you get at that curiosity. Imagination, what happens if? Resilience, not quite going well, I might have to go again. Self-regulation, ideas, perspectives and others, that's working collaboratively. Different ideas about the mathematics, about the project work that might relate to data. I haven't really focused on the use of data and the need for data literacy, but most of the data students will be interested in will come from their lives. So projects like Census at School, which has been going for over 20 years, just does regular censuses within schools, creates a wealth of data from children in schools all over the world to enable them to have real inquiry on the things that really matter to them. So I think these sorts of documents really prompt us to think about what is the direction of travel that we want to go in this country and obviously globally. And I've got this little clip, which I kind of just, oh, sorry, let me just go back. Oh, I missed my video. Come on. You're going to play. Yeah. Okay, I just want to show this because this is the sort of technology that is out there now. Which really says more than ever why those sorts of questions have really served their time. It's that quick. Lots of ways. How do you want your numbers presented? You can have them as improper fractions, you can have them as decimals. Elimination, substitution, which method do you want? It's all there, and it's that accessible, and it's free. So what are we teaching in schools? Can we do better stuff? Can we do stuff that really engages with the mathematical ideas, builds that conceptual understanding, and really invites children to build a relationship with mathematics that is going to stay with them in a positive way through their lives? And there's a host of different ways of doing this sort of work. So just showing you, the inputs can come from anywhere, but in another platform, moving on, we can be more exploratory with the same set of equations. So this is a piece of software developed at one of the US universities. And again, it's going to look at a set of simultaneous equations, but it allows us to do other things with them. And what's nice about some of these emerging technologies is it's handwritten. Right now, we are still handwritten in our exams, everybody. Those of you who haven't stepped in an exam room for a few years, kids are really still writing in paper and pencil. And with their, I haven't got my TI-82, with their graphing calculator on the side. But these are the sorts of technologies that just means you can open up the ideas, and we really do need to think about how we structure the assessment in a formal sense. So that's the assessments that are gatekeeper assessments for future pathways in education in a way that is really going to enable the students to build a portfolio of what they know and understand, but it just might not be in the current models that we have. So we could start with questions like that. Quite a complex one, this one. It took me a while, actually. Yeah, we can get there. Or we could put it in a new scenario. Still pretty much the same question, just a bit of context. Or we could just do something bigger. Open it up. Give the kids a chance to produce some mathematics that really shows the understanding with enough time to work on that. Go away and sleep on it. Come back. Everything doesn't always have to be done in 1 hour or 10-minute sections. Learning is long and slow. Learning maths is long and slow. And we really need to think about that dietary plate and the time that we need in some of those activities. So as I finish off, I don't want to give a negative picture of what's going on in terms of classrooms, because we did a recent survey of teachers in the UK. And though some teachers, we had about 228 respond in this survey, and they were using 96 different technologies in mathematics. 96. And obviously, it's really encouraging to see some of those. So Desmos is basically the digital antecedent of the graphing calculator. GeoGebra is another version of the dynamic software I was using. I used a visualizer. That's what you were seeing there. Promising, promising. But if we think about innovation as throwing seeds out, and we've got all different seeds from different plants, and each of those is an innovation, and some of them are daisies, and they sort of come up and hover around for a bit and then wilt and die. They might come up next year, but, hey-ho. Some might be dandelions, and these frothy little ideas have all flipped around, and some might be fir trees, and there might have been an acorn in there. And this is the world of teachers and school and maths and technology. The ideas come from all over. Some of them take root. Some of them really form very, very strong roots. And others come and go and they're forgotten. I think I counted about 30 different mathematical technologies I've used across my career. And each time I've had to unlearn and relearn, unlearn and relearn, move forward. Sometimes I still go back to old tools. But that idea that you find the tools, you need to find your oak trees because we do want most students to have some common experiences, but we also need to do that really important thing called exnovation, which is basically the opposite of innovation. We do have to chop things down and kill them off and say we're done with that. We did that to the logbook. We haven't had many exnovations since. We might do that to the age 16 high-stakes exam. I know a good one. What if we say kids who've come through primary school without the use of technology have such a command of calculation, let's allow children in secondary school to use calculators. That's an innovation in our current system. So I think we can do better than that. I hope I've showed you a few examples of how we might take some of the very established tools, think very small about what we might do with them, to really give students a rich mathematical experience through school mathematics that they remember, and they remember with really positive memories, like my Daniel. Thank you very much indeed.
Thank you very much, Alison, for that fascinating talk. I'm saying this as someone who's never had a single formal maths lesson in my life. There's a whole other story, but today is your day, not my day. So I'll tell that story. The fact that I am following your talk so closely and really fascinated by it tells us how wonderful, amazing educator you are. So thank you very much for that. Now, we have a very nice tradition for our IOE professorial lectures to have someone to make some comment as a respondent. And today, we're very lucky to have another Alison Littlejohn, to give us that commentary. Alison is Professor of Learning Technology, so it's very suitable, and has recently finished her term as a director of the Knowledge Lab, where Alison also works. And the Knowledge Lab is a great place for interdisciplinary work, and we have Richard, former director, here as well. Alison currently leads the Grand Challenge of Data Empowered Society. Alison, over to you.
Thank you, Liwei, and thank you, Alison, for a wonderful and very passionate inaugural lecture. One thing, Alison is a fantastic colleague, as many of you know, and I can't keep up with her. Put your hand up if anybody's found a way to keep up with Alison. No, nobody has. So, of course, the inaugural raises some questions as well, and what I wanted to do was to pick up on 3 key points that you made during your lecture. The first is the mismatch between technological advancement and educational change, because you mentioned that the pace of technology is fast, but educational change is really quite slow in comparison. So I want to pick up on this misalignment of the fast-paced technological change and slow organizational change, and to ask you, is this something to do with culture, identity, and values across these domains? And as you know, there's been a lot of criticism about the fast-paced technology company change from colleagues like Ben Williamson, Neil Selwyn, our very own Wayne Holmes, and others. So should culture, identity, and values of teachers be what drives us forward? Or should it be a cultural alignment, or should we not bother with culture at all? What are your thoughts?
Yeah, I mean, I think if we look into, and many of us have had similar journeys in our relationship with technology in the room, is there has to be a connection, and whatever the technology is, it has to be offering you something in your practice or in your work, your professional work as a teacher, that is of value and aligns with your values. And I think that's where you can't get away from, the culture of a school. If a school is really geared up for the high stakes at all costs, then there's less space, and the teachers have the message that they cannot innovate, or there isn't time and headspace to innovate. So in my ideal world, teachers would be at the table when it comes to discussing and working with the developers who have the skills and in some cases the funding to bring things to life. The closer the relationships, the better. I don't think it can be done from solely inside schools anymore, but at the same time we need better dialogue and opportunities to engage. And that's, I mean, the testbed work that Li Wei mentioned at the beginning is really trying to find the mechanisms that we can bring the teachers and schools much closer to the industry that is developing the technologies with researchers' support.
Well, that fits neatly with the second point that came from your lecture, and that is the critical role of teachers in digital transformation in the classroom. And you position the teachers playing a vital role in integrating technologies meaningfully. But you demonstrated, but I just wondered if you could unpack what is it that teachers should be focusing on as they adapt and use digital technology in the classroom?
Yeah, I'd never do a teacher should. That's not my nature. I think what we want to do is encourage innovation. We want to support opportunities for teachers to innovate, and that means in the system and structure we need to provide time and headspace for that. But you do need sort of sparks of inspiration and good ideas from somewhere. That's not to say that schools can't innovate, but you know, we all learn when we look outside of our own settings. Do you know one of the best initiatives we had in this country was Teachers TV? Who remembers Teachers TV? What an easy way to get innovation in the ether of the education system. So a lot of it is you don't know what you don't know. You can't know what you don't know. So if we don't have those collaborative opportunities and that opportunity to look outside now and again, I'm not sure how it'll happen.
Okay, so a third point that you made was about rethinking assessment in the context of mathematics education. So I just wanted to ask you a little bit more about that. The crucial point is that the assessment systems have to evolve, you say. But we had the pandemic, they did evolve, then they went back. So what's it going to take to make assessment really evolve and change the way we need it to?
Yeah. So I don't have good news on that one. I think it is extremely challenging. I mean, if we just take the England situation, there is no money in the system to bring about a big change. We are in the middle of a curriculum review, and sadly, it's limited by the fact that it can't really recommend anything that's going to cost money. So the big change is to cut down that oak tree that is the formal assessment. But the journey to that is going to be not anywhere near as fast as any of us would like. I think we have a real problem. So we have to really look at how we can provide the opportunities in the current system in the best way we can for now.
Okay, so now a point you didn't make in your lecture, which is probably the hottest topic in education at the moment. That is AI in education. Why didn't you mention it?
Just another technology.
That's a really good point. So what's clear is that you've really blended your knowledge of pedagogy, the learning science, the concepts and so on, to come up with new knowledge that you profess and which is really making a difference. I know that you haven't said anything about your impact, but I know that your impact has been incredibly strong, and that's always a bit of a challenge for academics. So, Alison, Professor Clark-Wilson, I just want to say huge congratulations, and I'm going to hand back to Li Wei.
Thank you.
Thank you, Alison. Thank you, both of you, for a fascinating lecture and fascinating evening. That concludes today's formal part of the event. You're welcome to stay and have a drink and continue that conversation with Alison. Thank you.
Thank you very much. Thank you. Thank you all for coming.